good morning. I'd like to add my thanks to the other speakers for the invitation to address you this morning, and like the last speaker, to apologise for my unusual accent. I'd like to take quite a different direction to the last speakers in geology and talk a little bit about the concept of sustainability that we're dealing with in the Sustainable Minerals Institute. Not so much to have a very abstract discussion, but rather to attempt to show you how we want to connect the production process, the environmental considerations and the community and workforce issues into a coherent way of dealing with things so that the, if you like, too easy methods that are not really operational for us can be put aside as early thoughts of sustainability, and we move towards more operational and perhaps more engineering-based approaches to, I guess, creating change rather than creating thoughts of change. I've shortened my talk a little bit for you this morning. I've removed this last section that I've added on the outline here around commercialisation. Now, the reason I had that there originally is that if the knowledge institutions and the conceptual development don't connect to the business of mining and the business of the future of communities, then it's an exercise that's very pleasant for researchers, but perhaps not very useful for long-term sustainability. And I'd be very happy to talk to people about our concept of commercial processes and transfer after the discussion. Just to give a little background, this is a very common way of viewing the sustainability issue in mining and minerals today. In particular, this little graph on the right-hand side, it's not entirely important what this is labelled with. The message is very, very simple. Globally, the quality of ore bodies is decreasing. Not every ore body is less than the one before, but on average for all commodities, the quality of ore body is decreasing. This has some very important consequences. The quantity of waste rock and tailings and spent heaps from heap leaching is increasing dramatically. The global demand for the commodities is increasing dramatically. So this means that eventually the environmental considerations for the production process and for the long-term legacies associated with mining will increase dramatically into the foreseeable future. The resources required to supply those commodities globally will increase dramatically. Now, we know this is well articulated in literature. You can hear it in very many conferences. What you can't hear is how that view, a material and energy view, essentially a production view, and the business view of mining can be brought together with a long-term view of the sustainability of a local region around a mine, or more generally as the Iron Quadrilátero or various areas in Australia where those regional consequences, short, medium and long term, are properly connected to that. So here's sustainability as we often see it, the so-called triple bottom line. What I've done at the top here, which is a little bit subtle I suspect, is oops, that's not what I meant to do, is I've put some commas in here. And that's because, very interestingly, if you look at the literature and you look at the discussion around sustainability and the so-called triple bottom line, it does a very unusual thing, a very unexpected thing, which it actually creates separation. It creates separation between the production process, the environmental considerations and the human considerations. And in fact what we want to do is to bring these things together. The reason why they've been separated is because it's very convenient. Intellectually it's quite a simple thing to engage with, and operationally, from the point of view of making reports, from making change, it's relatively simple to deal with these compartments. My thesis for you today, and the strategic direction of our institute in Australia, is that given the picture that I just put in front of you, where the increasing requirements for mining and the increasing demand for commodities, is this approach based on separate compartments simply won't be enough. It simply will end up being a mechanism by which we explain why we cannot achieve the kinds of goals that were previously set for energy efficiency, water efficiency and community outcomes. I'd like to make a footnote here to separate two concepts, I think, which are very important to separate for certainly the rest of my presentation. And that's the difference between sustainable development as a term and sustainability as applied to an industry like the mining industry. This may seem a little abstract, but I think it's extremely important that we understand and are clear that mining is what we call weak sustainability. The concepts that underpin original sustainable environmental management or sustainable ecological development are essentially around concepts associated with biological systems, so fisheries, forestry, agriculture. Now, why is that important? That's important because we can calculate and we can manage a system so that the inputs and outputs balance in such a way that we can take a yield on an annual or a longer basis that is sustainable in the long term. In other words, if we maintain the inputs to the system and we look after that system, we can continue indefinitely to take yield. We can take wood, we can take fibre, we can take food. This obviously is not true for an ore body. An ore body is a non-renewable resource at a time scale that's meaningful to human beings and production. And this is so-called weak sustainability. And in weak sustainability, essentially, we extract the non-renewable resource, and from that non-renewable resource, we create wealth. And then we redistribute the wealth. The process of redistributing the wealth is sustainable development, and the choices we make as to how we redistribute that wealth are really the core to whether we're being successful in the development component of sustainable development or not. When I use the term sustainability in this talk, I'm referring directly to the quality of the processes that we use to make that conversion occur. How well we deal with the environment, how clever we are about the energy, material, water and human uses of doing that activity. So it's extremely important that you're clear that I'm not talking about the development of society through the model that I'm about to put forward to you, but rather how we go about the process of doing mining. Now, the first step of thinking about that is to come to the conclusion that we're dealing with business. Sustainability often can become very idealistic, which is very useful, but not very helpful if you're a multinational mining company or even a national mining company. You have to run a business. So let's untangle the business a little bit first. So I'd say that any mining company can be thought of in terms of what I call the mineral commodity business. And these are people all over the world whose primary interest is in money. How money is managed, how money is well invested, and how returns to shareholders are realised. And many mining companies are actually run by people who know very little about mining. And that's fine because they know a lot about money. And as shareholders and as people interested in sustainable development, we want to ensure that the redistribution of that wealth is done very well. So we don't want a lot of that wealth wasted. So it's quite handy to have people who understand money doing that. I don't understand money at all. Money confuses me a lot. On the other side, we have where we focus our attention mostly, which is what I call the minerals extraction business. And that's this conversion of the non-renewable natural resource into a commodity that then the people who understand money can move it around the world and make money from it, and then make money from the money they make from that. So the goals are quite different here. The goal over here is conversion of financial capital and efficiency in that domain. The goal over here is a efficient conversion of a whole series of resources to extract that non-renewable resource and turn it into a commodity. And that's our core interest in this so-called sustainability of mining. That's why we end up with the eco-efficiency approach as the first stages of that. And then the humans manage it all. I won't say too much more about this, but we have a growing and very important research component in our institute about how the human management systems interact with the engineering systems and to some extent the financial systems as well. This is something that's generally overlooked. We generally think about mining as simply a mechanical and engineering process, which is very naive. So I'd like to separate the world now quite conveniently, but not quite accurately, into money returning value to shareholders on one side and the quality of the processes that we undertake, delivering reputation to that company and, to an extent, reputation to the communities and the regions within which mining occurs. So there's a vested interest between the companies and between the owners and stewards of the surrounding land. And in my view, that makes what I would call a valuable and sustainable company. So now I'm going to focus on this concept here, the reputation. I'm going to build a framework for sustainable mining on the basis of the growth, development and protection of reputation. And I'd like to think of reputation, and again from the business point of view, of the relationship between investment and return. Our investments in this case are around, they look a little like the triple bottom line in a slight restatement. That is, they deliver to your reputation how well you manage the environment, how well you're perceived to manage the environment. Similarly, for maintaining the cultural, spiritual integrity of regions within which you work. And then the ethics and principles that a company is espousing. You can find more and more often more and more companies that are putting forward principles of the way they believe they should operate as a company and the way they believe they should operate in the conversion of that non-renewable natural resource. Now, at one level you can say this is so-called greenwash. This is just a way of trying to deceive society that the mining companies are serious about sustainability. That may be true if everybody was trying to deceive everybody. But we've moved a long, long way in the last 20 years because it's no longer possible to deceive. People are reporting, people are measuring, people are auditing, and in particular the financial community is paying very strong attention to the reality of that auditing. The sustainable investment funds are now reaching multiple trillions of dollars per annum, and mining companies wish to attract that kind of investment as much as they wish to attract traditional investment. What are the returns from reputation? Well, this is not a religious or an idealistic view. If you have a good reputation, people want to work for you. They want to stay in your company. You can maintain skills. In a skills shortage, global skills shortage, that's very important to your business. It's very important to you in the long, short and medium terms. We all know that net present value is the basis of whether a resource is worth mining or not. A delay in the commencement of commodity production and therefore financial flows as a result is very, very costly. So if your reputation is very good from your performance in previous operations, the likelihood that your approvals will be delayed is much reduced. And that can be a very big return. And there are many documented cases of very slow returns, very slow approvals costing billions of dollars. We also want permission from both society and from government to access the resources required, the other resources required to extract the minerals. Water resources, we hear it again and again all around the world. It doesn't matter whether you're in an environment that has too much water or not enough water. Quality stewardship of the water resources, sharing of the water resources and the long-term security of those water resources for all users is a key concern to all communities, governments and increasingly to mining companies. So if you can gain access to land, access to water, then you have the potential to extract the ore body. Without those, you can't get with the best of engineering the most sustainable and efficient process happening. And finally, as I said before, shareholder attractiveness. Is this a company where I would like to see my superannuation invested so I'm comfortable when I retire that the profits I took from the people who are making money allow me to sleep well at night? And this is an increasing trend, as I said, around the world for people to do this. And one of the reasons is it's extremely simple to make that decision. In my superannuation scheme in the University of Queensland, on a 24-hour basis, by going to one website, I can change the proportion of the investment of my superannuation in high risk, low risk, more sustainable, less sustainable businesses. So how might we now consider this reputation from the point of view of assessment by society generally? And certainly this last point cuts to the discussion we're having about iron quadrilateral. What's left in the medium and long term after the extraction of the non-renewable resource? As I said before, we have the opportunity to redistribute wealth that's created, but we also have the opportunity to leave benefits and legacies in the communities, in the landscapes, that make the process of mining considered to be worthwhile more generally. And it's got to be said to be true that that's not the case generally with societies and local communities at the moment. Whilst there is respect and acceptance of the value of the money flows into community, there is not general acceptance of the long-term consequences associated with those value flows, and in particular the intergenerational component of the movement of that value. We see increasingly statements that water resources, again, water for example, in mining operations will be treated forever. So the only solution available to certain water problems, acidification for example, or other water problems associated with mines which do not continue to produce money, will be to put engineering solutions in forever. That's an absurd concept. It's absurd to think you can engineer anything forever. What is forever? 50 years, 100 years? We just see in geological terms millions of years. So we really need to be seeking ways of making sure that the engineering forever solution is gone. There's a challenge for researchers and a challenge for engineers that the way we go about the processes removes the need for forever treatment. The thing that we have to come to terms with, and this is cutting into the business again, is that if we want to leave superior legacies, we have to understand there's a difference in the time distribution of wealth. And this is very, very difficult if you're interested in capital, access to capital, discount rates and interest rates on capital, because you like to delay expenditure. And in fact, what we're suggesting is that if you are going to have legacies that don't last forever, in other words, forever for a discounted cash flow is 15 years from the point of view of what sits as a liability on a financial balance sheet. If 15 years is a blink, it's not forever. So we have to come to the realisation that we need to move money forward in the expenditure profile to reduce the legacies in the long term, to reduce the long-term massive expenditures. And so we have a really strong tension here with the financial systems that we're using with net present value calculations to make the investment decisions to mine. There's a very fundamental component of sustainability where if you're separating the economic from the other consequences of resource use, this won't change. And this is a very, very big problem, a very big global issue. So I have a little model. As scientists, we always like to draw pictures of everything. So the framework here, the basic framework that I put forward to you is that we can have a look at this relationship between the benefit flows we have, the legacies that we leave, and the amount of effort that we're prepared to put in at the time of development of mining. And now why do I say that again? Because from a cash flow point of view, a mining company wants to see expenditure related to cash flow. It's very unpleasant on a balance sheet to have a lot of expenditure coming into an operation that no longer is producing revenues. So we have again that same time-based tension on the value of money and the access to money. So I'd suggest in the past that the basic concept of mining was to extract the resource at the minimum cost and then to take the maximum revenue from that. Now society no longer accepts that, and governments on behalf of society no longer accept that. So really where we've moved is we've moved up into a state where we do put more effort into the way we manage mines in the landscape and the way we manage regions of mining, but perhaps we're only just starting to nudge above a neutral point from the point of view of those legacies, an acceptance that that redistribution of wealth for operations that are managed very well is becoming more accepted to society. This area here, what I call here the operations we have very much an efficiency, what I call an efficiency focus at the moment, and this is the triple comma, bottom comma, line approach. That we have an engineering approach that says if I'm very efficient with my energy, I'm very efficient with my water, I'm very efficient with my human capital, and I'm very efficient with my interactions with the community, then I'll become a sustainable mine. Now, the difficulty there is that the lack of connectivity between those efficiencies, we lose very large synergies, we lose very time-based, space-based and human interaction synergies. And as I said to you on my very first slide, my view is that it's very clear in the literature, there's very clear information that mines that we're running now at the lowest water efficiencies that we know and the lowest energy efficiencies that we know simply cannot find enough water and energy to meet the demands of the commodities of the future. So the efficiency-based view is extremely good for a continuous improvement-based view of sustainability. The issue with that is we've now continuously improved for around a decade, and we're beginning to tail off. If you look at sustainability reports that are being produced by companies worldwide, they are increasingly explaining why indices are not decreasing. Change of mining methods, more overburden, larger haul distances, longer distances for energy transport to and from mine sites. These are quite rational and good explanations as to why we're increasing the resources that we need, but they don't meet the larger goal of reducing the resources that we need to produce the commodities. We are not going in the right direction if you look at the overall consumption patterns. We are, in many cases, on many mines, going in the right direction from the point of view of per unit requirement. That is, how much energy per unit of material I moved, or how much water per unit of material I moved. But as we expand, the total requirement and the total use is increasing. It's not decreasing. So we need to be thinking about another place. We need to be thinking about another paradigm. We need to work through conceptually and to some degree idealistically that efficiency, we don't stop efficiency, we don't give up efficiency, but we begin to look at what might come from other views of connectivity, of linkage, of other ways of looking for synergies in these systems that will provide step changes. And then ultimately what I call visions of revolution, and visions of revolution have the sustainable word attached to it. So I can talk in some ways interesting in my head anyway about sustainability to you, but I'm unable to define this place out here. It's a work in progress. It's a general societal work in progress. And what we're doing at the moment is we're being very faith-based that individual parts of efficiency will automatically, with no more effort, lead to something we call sustainable. And in fact, a sustainability program could equal a 5% reduction in my energy use per unit tonne. That's by no means going to make any kind of automatic step up here. So what I'm suggesting is quite simple, that we need a transition, that is related to the connectivity of the system and the linkage between various parts of the system. That to think we can step automatically from here to here is not supported by engineering capability, conceptual development, or scientific fundamentals, or economic fundamentals. And we have no fundamentals for human systems and communities. There is no thermodynamics of humans. So we have no fundamental base to use there at all. We haven't tried to develop it, and we haven't tried to bring that into considerations of an engineering view of sustainability. So down here in efficiency, we have business improvements and technology. Some global experts believe that there have been 2 technology breakthroughs in mining in the last 100 years. One's called open-cut mining, and the other's called flotation, sulfide flotation. Now that's a bit mean to the engineering and science community. There may have been a few more breakthrough innovations than that in some people's view. But the question that's interesting to pose, the thought process that's worth going through here, is how many breakthroughs do we expect in the next 10 years to have sustainable mining, to reduce the energy and water footprints with increasing supply and increasing demand? And the answer can't be 2 breakthroughs. The answer can't be 1 or 2 major breakthroughs, because we can't even envisage what those breakthroughs would look like to design them. So we have to stop kidding ourselves. We're not investing globally. Mining companies do not invest globally the billions of dollars in innovation and research that would be required if they were going to get 10 or 15 breakthrough technology innovations in the next 2 decades. Now, why are the next 2 decades so important? The next 2 decades are so important because there are more mines in the pipeline for greenfields development and expansions now in mining companies globally than all the mines that exist. Those mines that are in the pipeline, assuming capital will flow to them, and there's no reason for us to think with China and India's demand that capital will not flow to them, look at the increases we've seen in the last 5 years, all of those mines will go through pre-feasibility in the next 5 years, say 10 years to be generous. The decisions on the major capital items and the way a mine will run is made at pre-feasibility, or let's say feasibility stage. So the tens of millions to billions of dollars capital investment decisions for the mines of the next 20 to 30 years will be made on the technology that we have available in the next 5 years. The chance of getting 15 breakthrough technologies to reduce our resource requirements in the next 5 years, in my personal view, has a probability of 0. So that means that if we're going to use today's technologies with some additions that we can't necessarily expect, or can't necessarily predict exactly what they are, we need to be very serious about the way of using the technology we have now to design, pay for, and implement mines that can actually get step changes. And those step changes will come by the smart ways that we use the technologies that we have now. Now, this may seem a bit pessimistic, but it isn't. It's not pessimistic because it's quite realistic on the concept and rates of ideas, moving to proof of concept, moving to engineering, moving to implementation. 20 to 30 years is the general time period from which an obvious idea becomes available. We could halve that time with excellent engineering and with urgency. We could halve that to 15 years. I would personally say the probability of bringing that to 5 years is again a probability of approximately 0. So in the next 5 to 10 years, we have to become much, much smarter about the way we put together the technologies we've got and the expectations we have for how they will perform in our landscapes, and have a very mature discussion with society about the implications of those two things. This is beyond sustainable development reporting that we see today. This is sustainable development dialogue. Do we want the commodities? Do we want the world development? How will we deal with the consequences? I don't really believe we're having that global dialogue in a very mature way. We're having it in an efficiency-based way at the moment. What I'd like to do is to focus on this, what I call effectiveness, this connectivity area, and now give you very quickly a series of examples that really are here to have thinking, to show that some of these linkages can return big results with really very little effort in many cases. I'm going to move through this space very quickly. This is simply a way of conceptualising where certain things that we manage now might be with respect to how connected those things are. So for example, a metallurgist, I don't know if there are any metallurgists in the audience, I'd like to pick on metallurgists. They have a view that any problem with the performance of flotation, for example, in a concentrator is simply to do with the reagent regime. And any problem can be fixed by changing the reagent regime. Now, it's a little unfair, but not entirely unfair to metallurgists. In other words, that whole resource and processes that came into the flotation cell are a little bit irrelevant to what happens within the flotation process and where the money comes from in the concentrator. And right up the other end here, we know this whole idea of closure planning is going to require all the disciplines that we have available to us, and across the operating environment here of the life cycle of the mine, the regions that we work in, and the value chain that we're working with. We don't know how to do that. We don't have a fundamental construct for that. We know quite well how to write frameworks for closure plans for mines. We can't illustrate a single mine on this earth that has been closed in such a way, that has been taken through a closure process that is a project process that an engineer who's proud of opening a mine would be just as proud of closing that mine. There isn't one. BHP Billiton is looking at their first one in Australia now as to how you take a project view to closing a mine, not a project management view as to how to write a plan about mine closure. I know this sounds a bit subtle and it sounds like I'm playing with language, but for those of you who are engineers in the audience, you'll see this is a non-subtle difference at all. That's the sound my phone makes when it rings, so I was a bit stressed there as my mine. Let's have a look at a very simple example. So here's a water quality trace, a time trace of water quality with rainfall in the bottom. It's very hard to see there, I'm sorry. The yellow on the slide here is the rainfall. And as you see, a very simple thing, when it rains, dilutes the salt, and then when it stops raining, evaporation, gradually the salt levels increase. So this is information that was available to researchers that was not known by the people in the plant. What happened when the salinity changed is the flotation in that plant crashed. They didn't know what to do. And as all good metallurgists, they added reagent. And as you can see here, the way they added the reagent, both the frother and collector that was added here, well, it's a bit random, isn't it? I mean, those guys were searching. They were just trying to get this plant back under control and get the flotation happening again. Now, every metallurgist knows that these were not clever metallurgists, because if they were clever metallurgists, they would have online monitoring, they would have a modelling system, and they'd have a feedback into automatic reagent regime. And so you wouldn't have random additions of reagent, you'd have a very nicely controlled system and a recovery of flotation. For those who are interested in effective mines, for those who want to think beyond the concentrator, this is where the water was coming from. A very large water body, a long way away from the concentrator, so it doesn't exist as far as metallurgists are concerned. And here are the water profiles at the time. So as you see, we had water at the initial concentration, the rain diluted that water, and then gradually, as I say, with evaporation, it concentrated again. The pump offtake for this was here. So we can get an automatic control, monitoring, feedback, simulation, etc. system, or we can drop the level of the pump intake. It's quite an effective way to manage and to just completely remove the existence of a problem simply by looking at a very, very simple linkage, linking the mine site and the management of water on that mine site to the production, to the operation, to the metallurgy. Now this is a radical revolution, folks. This means that the environment team on a mine site would be working closely with the people in the concentrator on the water system. Doesn't sound all that difficult. Doesn't occur very often. Let's look at production. Let's look at the production process itself now. Here's a very simple model that says the obvious, which is we have an ore body, and through a series of physical and chemical transformations we produce a commodity and we produce residues. Truth is, we really very rarely describe physical and chemical transformations. We actually describe unit processes, unit operations, and we do it more or less empirically. We've got a 50-year project that's been running in our organisation with Amira that was referred to today that has produced almost no phenomenological description of what occurs through crushing, grinding and flotation. But it gives you the world's class best simulation models for telling you how your operation will run through a series of empirical steps. Can it break outside those empirical steps and tell you about a radically different way to consider that processing given that ore body? It can't. It can't, because it's not thinking that way. It's not trying to do that. It's not trying to generalise this intersection here between the physical and chemical processes. It doesn't use thermodynamics. It doesn't use phase spaces. Why? Because it's difficult. It's difficult to do that. And the other why was that in 1962, when the project started, nobody understood comminution and flotation. So the first stage was to understand. Our next challenge is to move towards prediction and forecasting of other possibilities than the ones that are already in front of us. Let me give you an example here of what I call a connectivity pathway. So I'm going to connect blast design. through to the traditional mine to mill, which is blast design to comminution, and we've spent quite a few, probably decades now, with demonstration that mine to mill is a very effective way to reduce energy consumption and to improve the efficiency of a mine. We've also demonstrated that the human systems on mine sites seem incapable of managing mine to mill for more than a year or so. But we don't understand why, and we've never researched as to how to change that. So mine to mill has been very effective at being introduced to mines and very ineffective at being maintained over a long period of time on mines. And one of the main reasons I would hypothesise for that is the movement of people. Coming back to one of those things I put on a very early slide, how do you maintain and retain the workforce in your company on your site? It has direct money value, even just in the production sense that I'm talking here. We're then very interested in the idea of blast to float, so the liberation of particles and the quality of flotation now being associated with the way you go about blasting and the quality of the energy management processes. Now we're starting to talk about mine design from geometallurgy, that is using the ore body properties to redesign the mine rather than just having your mine design on the basis of grade. Well, why does that matter? That comes back to my first slide. The grade is getting so low in so many mines around the world that the cost is actually becoming the main driver for the thought of the mine plan rather than the value and price relationship with the grade. Once they come very close together, if you're basing your mine plan only on the value side of the proposition and not the cost side of the proposition, you can start to go financially backwards just through bad optimisation. And then finally, the University of Cape Town has a very interesting program in mine to metal, where you're now thinking right through the smelting and metal collecting process from the ore body properties. We're not quite there yet. Our first step, a little bit like I said with comminution, will be to do this quite empirically. The majority of this work is very empirical. And then hopefully the next step is start to look at the phenomena and the underpinning science that can support different sorts of thinking about the processes. We're quite close to some of this now. This is a terrible slide, but it's got a lot of things on it. This is a model that we've built simply by coupling together existing models of the unit processes. So now we're able to look at the flows of energy, water, recovery, grade, cost, right through the process from blast design to flotation performance. And to couple that through scenarios of different mine plans and to couple it through tuning and feedback processes to knowledge about the ore as it's being measured online from the mine. This is now being installed in a platinum mine in South Africa. This work was supported by Anglo Platinum over a period of 18 months or so, and is now the basis for a very large cooperative research centre that we've just starting in Australia on ore body optimisation of extraction, and Amira are one of our partners in that. So that's several $1 million, probably $15 million or so of government money that will be added to the industry money over the next 5 years to take this kind of prototype approach into an effective simulation environment that will allow us now to really think about how the ore body properties might be used to design mines on the basis of tracking each part through the system of where the energy and water is. Now, why is that important to my coupling process? That means now you should be able to get the first indications if you were looking for breakthrough technology just where you should be looking hardest. And if you were a brave mining company or a cluster of mining companies that were prepared to spend a few $1 billion to actually secure your future, you're now getting much better information for a range of mines on where you should target that gamble. So I'll flick through these examples. I want to go through. I've got, like the previous speaker, probably 2 or 3 hours worth of work. The representation here is an interesting scenario where what we see is the same rock in the ground with the same minerals in it, but we see a different mapping of the energy cost associated with that depending on the circuit that's used for crushing and grinding. So from an economic point of view, from a sustainability point of view, these are not the same ore bodies. We're starting to get these pictures through now for water and for other things as well. I'm going to skip right through a whole lot of these because I want to come to quite a specific example on water. This is an area where we've now used a whole of mine approach to accounting water across a whole series of mines in a region, to do two or three different things. The first is to look at the way the application of leading practice into each of those mines would shift the water balance of the mines to reduce risk. I'm sorry, I've gone too fast, too far. You frightened me with my 2 minutes. This is the plot I was looking for. Over here you see a series of curves that represent an integration of the water balance through time for each of these mine sites that shows you how full they are, how much of the time. It's a statistical statement of an exceedance curve for a mine site. This is important because mines that are sitting over here are frequently in risk of discharge. And if we had any mines down here, they would be frequently in risk of not having enough water for production. What we've done here by, again, having mine-level simulation capability, this is a different simulation tool to the previous one, is we've been able to look at the simulation of leading practice on these sites. That's leading practice from the point of view of efficiency, but also leading practice from the point of view of the construct of the mine site, how much storage it has with respect to its climate, and how it goes about water reuse decision-making. And you can see here that we've managed to reduce all of the risks that are, the mines that are at very high risk of discharge very often. All of those now have been collapsed down to a very similar set. In other words, there's some big advantages to the regularity with which management systems can be put in place on mines if the mines are well understood from the point of view of the way they're being managed, as opposed to somewhat random in their history and the way they've been managed for their water systems. So there is a second level of value in that. Now, when I take that out to a region where we connect things together in the region, we can now look at these same sorts of curves that would say that a mine down here that is looking very dry statistically and a mine up here that's looking very wet statistically have an opportunity to share water. Now, at the moment, water sharing between mines is a very casual and more or less random event. And in our landscapes, we definitely have mines that are quite close together where some have excess water and some have not enough water. And what we have here is, for that region, this is quite a large region. It's a funny little picture, but what you'll see is in the red marks here, these are mines that are looking for water, if you like, that are a little too dry. And then the blue ones, these are mines that potentially have water of excess. And we've gone through a formal optimisation algorithm here to look at, well, how much water might be tradable. There's no money associated with that trade at the moment, but simply looking at distance and urgency to trade. Why does this matter? Well, when you're in a region where you want to be efficient with those water resources and you want to share those water resources well with the other users in the region, then it's not a very smart industry that's sitting with blue dots all over the landscape. Not only do you not want that water on your site, that then becomes a discharge risk and a management risk for you. So the industry can really help itself with some reasonable engineering and collective negotiation over connectivity in the landscape. And therefore, again, moving out of the narrow efficiency view of the way they're running the water systems on these mine sites and taking a linked regional view on the way they're managing the mine sites. The final example I want to talk about is the relationship between landscape management of carbon through both carbon stocks and biodiversity, through water resources and through sediment management. These things are very clearly linked through the driving forces of water through the landscape and the coverage and protection of landscapes. I'm sorry, this is an extremely small map of Queensland. So Queensland is this part of Australia, and the region we're looking at is this one, which has this catchment here. The reason I've put that there is that this is a very large area that we've done this work on. It's not an individual mine site area. This is an area where there are very, very large reserves of coking coal, very large support of the Queensland economy, and irrespective of certain views of the use of coal for generating power and CO2, we haven't yet figured out how to create steel without coal. And so this is a long-term mining region for coal, irrespective of global changes and global views on mining of coal for power generation. The landscape here, as opposed to the landscape in this region that we're in at the moment, has been cleared and has been extensively grazed for nearly 100 years. Now that's important because the landscape has been very strongly degraded by a prior land use. And the Great Barrier Reef sits off the coast here, so the degradation of that landscape and the transport of sediment in these rivers is seen as a direct threat to one of the world's natural wonders, and coincidentally one of Queensland's most important revenue sources for tourism revenue. So we have a very large-scale economic tension here between the land uses of grazing and mining that produce sediment in the rivers and the land uses of fishing and tourism that want to use the clean estuaries and Great Barrier Reef production systems. So what we've looked at here is, I don't know what's happened to that slide, I'm sorry, it's a bit of a mess. When we look at different ecosystem services, that is the way the humans value the vegetation in the landscape, we've looked here at whether we would restore this landscape from the point of view of the downstream water quality as the primary objective, from the perspective of storing carbon in the landscape, if we wanted to start to look at carbon dioxide offsets, for example, for energy use on mines. And in this case here, this is just showing you the sequence of increasing investment from the point of view of restoring biodiversity to that landscape. The important point here is these are not the same spatial patterns. So optimising for one or other of these ecosystem services is giving you a trade-off to deal with. The reason that we're looking at it at the regional level is that the investment in mine site rehabilitation in this region in the next 50 years will probably be larger than the government investment in natural resources in this region by at least a factor of 100 and probably a factor of 1,000 financially. And so the question that we're posing is a very large question. Do we spend all of that money on rehabilitation of very small amounts of land, of very poor quality substrate, or do we look at this very large landscape and the amount of money we have and the values that might be returned in the very long term to society as a result of that investment? It's very difficult to pose that question to government and industry, to have a discussion or a dialogue with government about these questions if there's no quantification of the size of the prize and the size of the trade-offs that underpin that. And that's exactly why we're doing this work. We're doing this work so that the scientists can provide the information that will trigger the dialogue between government and industry. The quantification of that in this sense is the downstream water quality effect as you increase the restoration area. And the interesting thing here is that you can see that one of these restoration objectives has a quite different response to the other two. So there's potentially quite strong synergy between the other two from the point of view of the effect on the landscape. Whether they're in the same spatial areas, of course, is very important, because you actually have to go and plant the trees, not just run a model. At some point you must actually go out there and do something and not just stay in the laboratory. I'm going to go through very quickly, because I think I got 2-minute warning about 10 minutes ago. Some examples we have here of working through connectivity in the way a community and community futures would be dealt with right through a mining region. And in this case, it's where towns are created when mines are created. And then when mines close, what happens to the town? Does the town get closed if one person still wants to live there without a mine? 100 people, 1,000 people, 10,000 people? Who has responsibility for those services in the long term? What is the sustainability of that town from the point of view of its ability just to continue? Who supports the infrastructure? Or does the town get put in the pit with the final tailings? How do you make those decisions? And this is a piece of work that we've been doing with Rio Tinto, and I'm not going to walk you through it other than to say we did it and it's wonderful. This is the disadvantage of all these animations. So I conclude more or less where I started, that the next mines we're going to have in the world, by the way, some of you will know that one mining company has trademarked the term mines of the future and is actually taking a research group in Scandinavia to court over their use of that term. So I've never used the term mine of the future. I use this term I've called next mines. The Sustainable Minerals Institute has trademarked this term, next mines, and we invite anyone in the world to use that term whenever they want. They will be operated and run using today's technologies. I've made that argument. I think it's a correct argument, and the only thing that will make it different is if we slow down the development of mines and wait for breakthroughs. That means the world's financial markets and supply and demand economics being fundamentally overturned in the next 5 years, which I suspect has a lower probability than getting all the breakthroughs in the next 5 years. We know that community is demanding, and in fact mining companies themselves are demanding improved performance, and the engineers and scientists' challenge is to provide the capability to do that. They are step changes. Whether they happen smoothly or whether they happen as a step, it's not too important. The rate of change that has to occur in the next decade to 2 decades is huge. And as I suggest, step changes based on technological breakthrough are extremely rare. So my thesis, as I started, is that step changes based on making connections and making linkages in space, in time, within business, and between human systems has the potential to deliver synergies that are step changes. And I've illustrated some of those. And I believe that's where sustainability, in the way that I've defined that term, will become available to mining companies, mining regions and their communities over the next 20 years. Thank you.
Queria agradecer muito ao professor Cris Moran, invite you to stay here, e convidando também os outros palestrantes para se juntar à mesa para a parte de debate. E o Cris, nessa última palestra, ele trouxe muitos pontos para enriquecer o debate, não só na conceituação do que é sustentabilidade para o setor mineral hoje e no futuro, mas também nos grandes desafios a serem enfrentados para que essa sustentabilidade seja atingida.